Welcome to solverfy.
Okay, so we're doing chapter 22, problem 35 here. So this says a thin cylindrical shell of radius R1 is surrounded by a second concentric cylindrical shell of radius R2. The inner shell has total charge Q, and the outer shell total charge negative Q. Assuming the length L of the shells is much greater than the radiuses, much greater than R1 or R2, determine the electric field as a function of R for different distances. Okay, so since we're talking about cylindrical shells, we're going to be using a Gaussian cylinder around our shells here to solve for this. And we kind of talked about this in the solution for 33, so if you're confused, go back to that one first. But we can see that Gauss's law here, E dot dA, if we make our surface a cylinder or surrounding the cylinders, we can see that the electric field is going to be perpendicular at all points. And now we pull the electric field out times the surface area. And this is equal to what Gauss's law says, which is the charge enclosed over epsilon naught. Meaning that a Gaussian cylinder has an electric field that's radial and goes as Q enclosed over 2 pi epsilon naught RL. So this is what we're going to use mainly, and we might need to go back and look at different examples following 22.6 if you're confused at this point. Example 22.6 in the book. Okay, so for part A, we're trying to figure out the electric field for R less than R1. So for this case, we should see immediately that the charge enclosed is 0. So obviously the electric field is 0 for this case. Okay, so moving on to part B, now R is greater than R1, less than R2. Sorry, that is just a, oops. That should just be R there. Perfect, okay. For this case, we got to figure out what our charge enclosed is. Well, if we're drawing our Gaussian surface here, it means we're enclosing all the charge on the inner cylinder. So that means our Q enclosed is positive Q, because that's what was on the inner cylinder. So then our E becomes Q over 2 pi epsilon naught LR. Awesome. And this is positive, so we know it's directed radially out. Cool. Let's do part C now. So C is for R greater than R2. So in this case, our charge enclosed is the charge on the inside cylinder plus the charge on the outside cylinder. But that's just Q minus Q, or 0. So if our charge enclosed is 0, we already know, as part A, the electric field is also 0. Cool. And now part D, what is it saying? Part D asks, what is the kinetic energy of an electron if it moves between and concentric with the shells in a circular orbit of radius R1 plus R2 all over 2? Okay, so we should know that the force on an electron is given by the charge times the electric field. So if we should see that our R now is greater than R1 and less than R2. So our electric field in this case is Q over 2 pi epsilon naught RL. Okay, so we can now set the force equal to the centripetal force if we're moving in a circle, which is mv squared over r. Okay, so if we know this relation and we're trying to find kinetic energy, which is 1/2 mv squared, let's see if we can pull that out somewhere. We can say mv squared is eq over 2 pi epsilon naught L. So 1/2 mv squared is going to be eq over 4 pi epsilon naught L. So this is our kinetic energy. Awesome.